Good afternoon, class. This is a short video lesson on section 3.2, determining or finding the maximum and minimum values on an interval of a function. It's from your chapter 3 textbook, and I will post this video lesson in the detail course later this afternoon as soon as I'm finished. Okay, a couple of definitions before we start. Functions and graphs of functions will have things called extreme values over a defined domain or the entire domain. These extreme values are special points on a function. At times they can be minimums, maximums, they might be turning points. They're basically a point on an interval or on an entire domain where we want to look a little bit more closely at. Could be an important point in the data where something is happening on the function. More specifically, the functions have a global maximum and a global minimum. A global maximum and a global minimum is exactly what you think it sounds like. It is the highest point on a domain interval, okay, or on the interval of a function. It's the absolute. It's also called absolute, right? Absolute maximum or global maximum on a function. Here's the definition for it. And functions can have a global minimum. It's the absolute minimum value on a function. So let's take a look at the definition of a global minimum here. It has to be the lowest point on the entire domain. Okay, definition-wise, we often state just the value. Okay, so f at c, or that's the y value, or we call the actual ordered pair point. And it means that okay, the value at the function is the absolute lowest value here. Here's the inequality right here, right? It's the absolute lowest value, okay, on that function. So every point on the function, okay, is greater than the actual point at the function. Okay, so we will be finding these today: global minimums, global maximums, or absolute minimums or maximums. Okay, so on this example, what's the extreme? Okay, it's the extreme points represented by these functions. Okay, so we I guess need to talk about not only global maximums, okay, but also local minimums and maximums. So first up, our defined function, okay, is on the interval -6. Okay, so -6 to +6. Okay, there's the interval here. All right, A is what we're going to classify as a local maximum. Okay, so local is a new term as well too, and the local, A, is going to be called a local maximum. Okay, so the local maximum is just found within sort of this local area here. It's not the global maximum. C looks like it's the global. Actually, no, not C. F is the global maximum. It's the maximum value on the entire interval. A is a maximum. It just happens to be a local in a local area here. Okay, B is a global or absolute minimum point. Okay, it clearly is the lowest point on the whole defined interval. Okay, next up is C. Let's do it in order. C is a local maximum, okay, for the same reason that A was a local maximum. Okay, D looks to be like it's a local minimum, right? Local minimum. It's a low point. I'm going to assume that the area past D or to the right of D tends to go upwards, and it looks like in the neighborhood of point D, everything is above D, and D is the lowest point. The actual point D is the lowest point, but only in this local area here. So I'm going to call D a local minimum. Okay, next up is E. Point E. E, it's not much, really. I don't think it is. It's On the left-hand side of E, it's low. On the right-hand side of E, it's above E. And it looks like E is just, okay, a point. Point on the function, okay? Common, let's just call it a common point. Now, we're not quite ready to talk about inflection points yet. You might be familiar with the term from advanced function. An inflection point is a turning point, and I think E might just very well be that turning point. I don't know for sure yet. There is a derivative test we can do with that. It's left for chapter 4. E, though, looks like a change point, right? It looks like E, at point E, it looks like it's gone from a concave up sort of situation, or maybe a parabola. And then at E, it changes to a straight line. It certainly, from chapter 1, it certainly is a point of continuity, but it looks like almost a piecewise function. E would be an important point on my graph, okay? But with respect to global and local minimums and maximums, it's really not anything here. Okay, and then F is finally, okay, it looks like an absolute maximum. Okay, so all functions in domains, in full domain or restricted intervals, all functions will have a global minimum and a global maximum, one global minimum, one global maximum, and they might have a number of local mins and local maxes. Okay, just need to turn the page over. So how do we find these points? Okay, well, it's not really that difficult to find extreme values here. Okay, so first up, we go for we get going. Maximum and minimum points are called extreme points, and at times extreme points might also be local. They're within a certain domain. So how do we find them? Here's a little algorithm for finding these. Okay, to find an extreme point, either global or local, for a continuous function over a closed interval, take the derivative of f and determine the critical points. And that's when you take the derivative and you set it equal to 0. Okay, now you might have a couple of values here, these turning points. Now keep in mind this concept that we've been talking about here, that maximum or minimum has a slope of 0, right? The tangent line is a flat horizontal line. So that's why we take the derivative and set it equals 0, because what we're doing is finding the places where the slope is 0. The slope of that tangent line is 0. So that's the first thing we do, and that's a pretty easy process depending on what the function is. We've been doing lots of derivatives. Okay, and then we evaluate the function. We just go back to the original function and evaluate the endpoints. Okay, so that's evaluating the function at A, evaluating the function at B. That's from here. Okay, and then we also evaluate the function for all the critical points, all the f at c values here. And then we just look at them. Okay, and we determine which one's the biggest, which one's the smallest. Those would be the global minimums and maximums. And then we classify the local mins and local maxes, looking at what's happened. We almost treat it like a sign chart in a sense. I won't be having you guys do sign charts with this, but we really analyze the function in that regard. So let's do our first example here, a nice easy one, okay? So I have to evaluate, okay, I've got this function, f at x. First thing I'm going to do is find the derivative here. Okay. Okay, struggling even at home. Okay, 12 x to the power of 3 minus 12 x squared. Okay, make sure that's good. Okay, so let's find the first and few critical points here. This is the solution I want to try and solve. So that means I have to solve this expression. Okay, let's solve by factoring. 12x squared would be x minus 1 equals 0. Okay, therefore 12x squared equals 0, or x minus 1 equals 0. But the only solution to this is when x equals 0 and when x equals 1. Okay, just a quick check. Does x equal 0 fall on this interval? Yes, it does. Does x equal 1 fall on this interval? Yes, it does, right? 0 is contained in the interval -1 to 2. Remember, this is okay, the particular way it's given, okay, is interval notation, this is set notation. So these are all, x is defined on this function for all values between -1 and +2. And there's two critical points, x equals 0 and at x equals 1 on this interval. Okay, so the next thing I have to do is, let's do it in order as well too. Let's start at the very lowest one, that's -1, and then let's take f at 0, let's take f at 1, and then let's take f at 2, and we'll sort of look at this from left to right. So now I have to go and find the value of the function at -1, the value of the function at 0, the value of the function at 1 is my next point, going from left to right, and the value of my function at 2. Now, I don't think this is hard for students at all, absolutely. You might just need a quick reminder here. So what I do, I'm trying to find the point on the function at -1. So I take my -1 and plug it into my original function up here. Okay, I've done the calculations. So when x is a -1, I found this to be, I'm just going to show you the steps here, but I'm not going to do this again. I'm just going to give you the values. Make sure you do this carefully though, because it does matter here. I got that to be 7. At 0, I got it to be 0. Okay, at 1, I got it to be -1. And you guys should go through that and validate that. And at 2, I got it to be 16. Okay, does that give us enough? Can we classify these? And I'm going to just change my marker here, okay, and classify these. Okay, so what's happening here? Okay, identify the absolute lowest one. The lowest value on this interval is at -1. So that's going to be my global minimum. Okay, or my absolute minimum, I call that, right? Okay, what's the highest one? That's down here at 16. So when x equals 2, y or f at 2 equals 16, that's going to be my global max. Okay, now these are also called absolute. Okay, let me try that again. Okay. Absolute, they're also called as well too. Okay, so what's the other ones? Okay, well 7, okay, when x equals, let's look at it this way. These are going to be locals, okay? At -1, okay, so going from left to right, I have a value of 7, and then when I skip over one point along the x-axis, I drop down to 0. So clearly I'm decreasing, right? My function's decreasing on this interval. So this, okay, will be a local max, okay, and this one would be, okay, a local. No, it's not a local min. At 0, I was going to say it drops down to 0, but it continues to even drop down to -1. So it's, okay, nothing but maybe a turning point here. But again, I'll save that for chapter 4. We don't really know. The function on this defined interval has a local maximum, and it has a global min and a global max. Okay, if you like, graph it in Desmos and see that, but restrict your interval, please. So some people like to do it like this as well too. They like to, okay, draw it on a number line or on a graph. A number line is really just the x-axis, okay, and a sketch here. So let's do it this way. So at -1, I'm at 7. At 0, I'm at 0. At 1, I'm at -1. And at 2, I'm at 16. So that's kind of what it looks like here without the red. Without the red dot here. Okay, so that's kind of what that would look like within that interval, but you can check that in Desmos as well too. Okay, I want to try another one. Okay. You guys, I'm going to leave you to try this for a minute. Okay. First thing you do, I'll walk you through the steps. First thing you do is you find the derivative, set it equal to 0 and solve for x. Okay, and you can graph it. You can always graph it and see. Okay, we're going to have to also then check these points here, right? That's exactly how we try and do this here. So there's a little bit of work here. Okay, the derivative is the quotient rule. I'm going to do the derivative quick here. Let me do the quotient rule up here. X squared minus 1, that'll be 2x. And x squared plus 1, that'll also be 2x. So my derivative, using the quotient rule, okay, is 2x x squared plus 1 minus 2x x squared minus 1 all over x squared plus 1 quantity squared. Okay, I'm going to leave it unsimplified and use this concept here, and we've talked about this in class before. This is ultimately what I'm trying to find when my derivative is equal to 0. Well, I don't really have to simplify this. I do know that my derivative happens to be a rational, it's a fraction, and the only time a rational expression or a fraction equals 0 is when the top equals 0. And the top is this, unsimplified. So our energy and our focus can just be on the top, and I have to solve this. Okay? Now, when I also don't simplify it, I could take out a greatest common factor. To me, it looks like, okay, my greatest common factor is 2x, and that would leave me with x squared plus 1, take away x squared minus 1, that equals 0. Okay, this is smart math, okay? So now I've got 2x, and then in my brackets I've got x squared minus x squared and 1 plus 1. So I've got 2 basically, and that equals 0. So I've got 4x equals 0. I don't even have to multiply that. So x equals 0 is my only critical point. The only place that this derivative is equal to 0 is when x equals 0. Okay, so now I've got 3 points to check. I think I should just scroll up and make sure I know what my domain is. It's my domain. -1 and 3. My 0 lies on my domain, so I have to check f at -1, f at 0, and f at 3, and just classify them as which ones are global mins and maxes, which ones are local mins and maxes. Okay, a little bit of work here. Make sure you plug in -1 into your original function. That's this original function right here. Make sure that you don't get crossed up with the derivative function. Okay, so at -1, I'll show the steps. First, okay, what have we got here? That's 0 over 2, or 0. I did the work already on a sheet of paper beside me here. F at 0 works out to be -1, and f at 3 works out to be 8 over 10, and I'm going to just simplify that to 4 over 5. Okay, I'll leave the math for you guys. Okay, which one's which? Okay, graph it in Desmos and confirm it, or just do some reasoning and thinking. If you want to do the number line, you can do that number line as well too. Okay, with an x-axis. So at -1, what's my value? It's at 0. At 0, it's down to -1 here. Okay, and then at 3, it's up to like 4 over 5 here. And if I want to draw my y-axis, I can. Okay, so it looks like my function is like this. Okay, so which one's which? Let's classify. I can just do that by looking at them. This one looks like it's the global, or absolute. I'm going to call them both. You'll see them in the textbook expressed in both ways. And again, they're all called extreme values here. -1 is the global, our absolute minimum. That's the low point on the entire function. Okay. And at 0, that's just a local maximum. Now it's a local maximum because it's on the one end of the boundary, right? Okay, on the restricted interval, and then after that it starts to go down. The function starts to go down to -1. So that's the high point, and after that it's going down. Keep in mind that nothing exists beyond -1 here. The function's not defined for that. Okay, think you got it? That's what you're going to be doing here for this homework stuff. Okay, one hard one left, and well, I'm shooting for 30 minutes, and I'm at 20 minutes here. So, okay, good. Here's a tough function. Okay, now I'm going to do the derivative in a different way, sort of on my own way here, and that's a pretty challenging derivative. So let's take the time and do that. Okay, the interval is very tight, very restricted. Okay, 0.5. Okay, so I have got, okay, to take the derivative first. Okay, let's stay in red and find this derivative. Okay, so this is going to be the product rule, right? See that? This is a product right here and right here. So my product let's try that again. That'll be 2x plus 1. Okay, to the power 1 times 1, I'm just going to leave it like that. I don't need really, okay, so that's kind of irrelevant. And then I've got x minus 1 to the 1/3. This is going to be a little bit harder here. Let me erase just to give me some space here. This one's going to be a little bit more challenging. Again, this is before the March break. So this is 1/3 x minus 1 to the negative 2/3. Now don't forget to take the derivative of that. It's just 1. Okay, that's fine, but we can leave it like that. Okay, so my derivative is my product rule. No. 2x plus 1 times x minus 1 to the 1/3 plus x plus 1 squared multiplied by 1/3 x minus 1 to the negative 2/3. And I have to find when that's equal to 0 using our strategy from the last example. I'm not going to expand that. I'm actually going to try and solve it by taking out a greatest common factor. All right, I think we can do it. What do you see for a greatest common factor here? Well, I see a couple of things. Let's take out an x plus 1. And let's also take out an x. Let's try this. Let's take out an x minus 1 to the negative 2/3. Okay? So I see something common, x plus 1, and I see an x minus 1 to the negative 2/3. So that effectively is going to get rid of this little piece at the end here. Okay, so in my front expression here, this first piece up here, okay, so I'm dividing this term, by this factor. Okay, so I'm left with a 2. My x plus 1's cancel each other out, and I do 1/3 take away 2/3, and 1/3 take away 2/3 is 1/3 plus 2/3. Or sorry, I got to correct that. It's 1/3 take away negative 2/3. So a take away a negative becomes a positive here, so that's 1/3 plus 2/3. That would leave me with an x minus 1, 3/3, or 1, right? Okay. And then I'm left with, okay, now let's focus on the second piece here. I've taken out an x plus 1. I'm left with a 1/3 factor. I'm just going to move it, and an x plus 1, and that's it, nothing. Okay, because I've actually factored out, okay, this whole thing here. So let me just, before I do and go much further, I'm just going to confirm that that's my factor. If you'd like to check that, distribute that in here. Okay, good. You can pause this here and make sure that you've gotten that. Okay, let's clean this up a little bit. Okay, by simplifying and collecting like terms of the expression that's in the middle. That'll be 2x minus 2 plus 1/3 x plus 1/3 equals 0. Okay, further, take that one step further. Okay, I've got 2x plus, okay, 2x plus 1/3 x, so that's 2x is like 6x over 3. So 6x over 3 plus 1 over 3 is 7 over 3x, and then a minus 2 plus 1/3, and that's a little bit harder. Minus 2 is like negative 6 over 3, plus 1/3, I'd have a negative 5 over 3 equals 0. Okay, so I have 3 pieces. Okay, so what are my values here? Okay, what are my values here? Okay. So I have x plus 1 equals 0, or x equals negative 1. I have x minus 1 to the negative 2/3 equals 0. Okay, and that's, looks like this, a negative exponent. Okay, well, there's no solution to this. Okay, a reciprocal function, you guys know the reciprocal function, 1 over anything never equals 0, so there's no solution here. We have a solution with this one, and then I have to solve this expression. Okay, well, that's easy to solve. I like doing this strategy. I can get rid of my 3's by multiplying everything by 3. That would be 7x equals 5, or x equals 5 over 7. Okay, that's my other answer here. So I've got x equals negative 1, no solution, and x equals 5 over 7. Before we go any further and check these points, let's see if they lie in the interval. Remember this interval? Okay, and do my solutions lie in that interval? That interval is pretty tight and small, 0 to negative 1/2. Negative 1 is not, okay, not in interval, okay, and neither is, okay, 5 over 7, not in interval. 5 over 7 is greater than 1/2. Okay, so we went through all that whole process to find the critical points, and we found our solutions. Well, one was no solution, but we found our solutions, and it turned out that they just weren't in the interval. Okay, so we still have to go through the critical point process. We don't know that they're not going to be the interval until we find them. So now we just got to check f at 0 and f at 1/2. Okay, f at 0, let's clean that up a little bit. It doesn't look like a 0. Okay, so go back to your original function and evaluate it at 0 and evaluate it at 1/2. Okay, I use Desmos for this, approximate. I think this is probably a good time to do that rather than fiddle with this function. If you go into Desmos and graph the original function, graph this original function, and then in the next window, type f at 0 and f at 1/2, you can actually get that as a calculator and use it as a calculator. You get, okay, this to be negative 1, and you get this to be approximately negative 1.78. This one is the global maximum. It's the high point, and this one's the global minimum. I've got a few minutes left, okay? That's how we do this. Okay, oh, there's my Desmos graph right there. Okay, I have it in here. So there's my original function, and remember that tight interval restriction, right? It was, okay, it was pretty tight, 0 to 1/2. That's, okay, just right in this area here, and there's my point and my point here. It was 0 to 1/2, pretty tight interval. I'm going to open Desmos up. It might take a minute to launch as we're finishing up here, but I'm going to open Desmos up. I think the next slide is the homework. Okay, we're good. Okay, I want you to fiddle around and play with those over the next couple of days. Build a good foundation, because that last part of the chapter is a very small chapter. The last part of the chapter, 3.3 and 3.4, is a lot of word problems and solving problems. Okay, I'm just going to close that off. We can meet again on Thursday and answer some homework questions, but I am going to call up Desmos and show you how to use it as a calculator here. Oh, open fast. That's good. Okay, so my original function, F it, okay, okay, and it's x plus 1, okay, to the 2, okay, and then I'm going to use my keyboard, okay, and go here. Actually, no, I'm not going to do that. I'm going to go, show you guys how to, you can use this feature. So I have to type in my index here is 3, and then I go underneath, and that's x minus 1, but I'm going to use brackets. Okay, so there's my original function. Now, I think if I recall, how do I do this? Okay. 0, 2, and then I close my brackets. Okay. And I can zoom right in, and there's my little function. Now I think I can, okay, use my calculator here. Oh, if I use it as my calculator, okay, I have to get rid of my interval here. So I'm going to get rid of that interval. Okay, so I can use that as my function and just sort of focus in this range here. I'm sort of using that as my calculator. And what was my other one? 1/2? No, it was yeah, 1/2. Okay, and I get, okay, just what I thought, negative 1.78. I think I probably used that. Okay. Okay. Now I can, okay, restrict my domain if I want to and do that. But again, the focus is right in here. If you use Desmos to use it as a calculator and get the values, you can't restrict your interval. If you don't use it for your calculator, you can use that interval restriction. And you just use curly, squiggly brackets here and inequalities here. Okay, that's it. Good. I hope that works okay. Please, again, check the textbook. Check the textbook for examples. Try the homework questions, and also review my D2L class lecture notes that will be immediately underneath this video. Good luck with this, guys, and feel free to join me on a homework question and answer session on Thursday, probably around 10 o'clock again. That video session will be recorded for future use if students can't be there and join us. And what else? That's it. That's all. Email me with any questions. Thank you. Have a good day.